grade 10 we were taught to grab a marker. Okay, we have m squared times m cubed. 2 bases, 2 exponents, what do you do with them? Add them.
Yep.
So you get m to the 5. And there's another one, more complicated example on the other side. So m to the 2x plus 1, more so what we're going to get in grade 12, m to the x minus 3. So we have 2 bases, 2 exponents. What are we going to do with those exponents? Add them. So we're going to get m to the 2x plus x is what? 3x. It's over here in this table on your notes. Mine hasn't showed up yet. And then 1 plus negative 3, negative 2. Okay, the next one we have 2 exponents but division. So we have m to the 4 divided by m to the 7. What are we going to do with the exponents? Subtract. Yeah, m to the 4 minus 7, which equals m to the 3. And then negative 3. And then we have, I'm waiting for the smart notebook to show, because there we go. Okay. So then we have the more complicated example over here. M to the 2x plus 1 divided by m to the x minus 3. Now you have to watch yourselves, because when you have this one, we had adding, it doesn't matter, right? But when you have subtracting, you have to subtract all of the stuff behind the subtraction sign. So we could show the intermediate, I picked a different one. We show the intermediate step, so we're going to get m to the 2x plus 1, technically minus x minus 3. You see how we're minusing the whole thing? Think they'll have the answer if you just minus the x and not the 3? They will. They'll be wrong. They'll have to. So we get m to the 2x minus x, which is x, and then 1 minus a minus 3, plus 4. Because minus a minus 3 is plus 3, correct? Yeah. Negative exponents. We were taught that we can move any negative exponent to the positive exponent by moving it to a different place. So, for example, if I had 1 over a to the negative 2, all I move, even if I had like a 6 down here, let's do this because people get confused with that. Is the 6 to a negative exponent? No, the 6 is to a 1. That a and that 6 are not attached. That's a multiplication symbol, right? So if I want to move this a and make it positive, I can move it to the numerator, but that 6 stays. So I'm going to end up with 1 over 6, and the a to the negative 2, when it moves to the numerator, becomes a to the 2. Becomes the opposite sign. If you don't believe me, let's do this. Ivan, your earbud has to come out. So we get 1 over... What? No. Let's go 4 to the negative 1. Type that into your calculator. Ivan, Paula. Let's put it on this table over here. Sure, you won't be the last. All right. 4 to the negative 1, did you type it in? What did you get? 0.25. It's over 1, correct? Now we can take this number and we can drop it to the bottom and it'll become what? 4 to the 1, which is 1 over 4, correct? 0.25. What a coincidence. So, if I have 2 to the negative x, how could I rewrite it? 1 over 2 to the x. Okay, 1 base, 2 exponents. 1 base, 2 exponents, what do I do with the exponents? Multiply them. So So this one up here was 2 bases, 2 exponents add, correct? 1 base, 2 exponents multiply. So I get m to the 6. Same thing here. I just have to remember to multiply all of them. So I'm going to get m to the 6x plus. What's anything to the 0?
0.
Nope. 1. Smiley face to the 0 is 1. So, yeah, anything to the 0 is 1. So, we do 3 times 2 to the 0. It's going to be 3 times what?
1.
So it equals. Then rational exponents we also did in grade 10. 3 to the half is the same as what? Do you remember? In a root. Square root of 3 to the 1. Remember, this just comes underneath and becomes the index. So it would be the square root of 3 to the 1, which is just the square root of 3. What's this one going to be? 8 to the 3rd. What's 8 to the 3rd? Cube root of 3. Cube root of 8, sorry, to the 1. Which is just cube root of 8, or 2. Okay, 16 to the 2/3. What's that the same as? The square root of 16 cubed. Now what you could do is you could put the 3 underneath, but now I'd have to do 16 cubed and take the square root of it, which I can't do in my head. Or you can write it as the square root of 16 cubed. What is the square root of 16? 4. Cubed is 64. So I can actually do that in my head if I leave the cubed out.
Are you answering it?
Yeah. All right. We want to write these ones with positive exponents. So I have 4xy to the negative 3. How else can I rewrite this? 4x over y to the 3. What about b? (15 over 5y), and then that'll drop down here, y to the 3. Do you see how I didn't move the 15? Because the 15 isn't to that exponent. So what's 15 divided by 5? You can get a 3 up here. 3 over y to the 2 bases, 2 exponents. What do I do with them? Okay, you guys try C, D, E, F. So, I would actually not change these to negative exponents positives yet. I would multiply it first. So I get 15. X cubed times x to the negative 2 is x to the 1, because you add exponents. And then y to the 1, y to the 4 is y to the 5. Okay, 24 and 16. You can take an 8 out of both. This will be a 3, this will be a 2, and then these will swap. So we get 3p cubed over 2p to the 8, right? And then the p cubed, take off 3 of these and left with a 5. So it's 3 over 2p5. And then this one moves up here. Is that mine? Oh, it's okay. I don't know why they put the sauce things on them. Thank you. So it's 2a to the 3rd. And then this one, so 2 to the 3rd, x to the negative 6. 2 to the 3, sorry. X to the negative 6. And 2 to the 3 is what? 8 over x to the positive 6. Okay. Flip over.
7,000.
Okay. We're not worrying about any of these. It's not a big deal. We're going to go to the next page. Okay. Okay. So we're going to look at exponential functions, graphs of exponential functions. So the format that we look at for an exponential function of an equation is y equals a b to the x. Everyone writing that down? That is our basic exponential function. If there's something added to the x's or y's, then we have transformations. Yeah, we're going back to transformations again. Never leave them. They're always here. So, here we have, consider there are infinitely many possibilities for b, and therefore infinitely many exponential graphs. So that b could be so many things. The key thing about b, though, is that b can be between 0 and 1, so like 0.25 or 3/4. And b can be greater than 1. B cannot equal 1, b cannot equal 0, and b can't be negative. So the key things is that b can be between 0 and 1, or b can be greater than 1. That's the limitations on b. A can be anything. All right? So we're going to look at y equals 2 to the x. And if it's in this format, we still have an a. The a just happens to be a 1 in front. 1, 2 to the x. Correct? Like that's the only difference. We've got that 1 sitting in front. All right. Let's look at the graph of it. So if we have y equals 2 to the x, then these are our x's. We're just going to plug them in. So our y is going to be 2 to the negative 3. Right? Input tables, output tables. We've done these since junior high. 2 to the negative 3 is the same as 1 over what? 2 to the 3. To the positive 3, right? Because I can move it to the denominator and make it positive. Right? Which is 1/8. So at negative 3, we're at 1/8. Slightly above. Okay? Then let's look at negative 2. So y equals 2 to the x, so y is going to equal 2 to the negative 2, which is the same as 1 over 2 to the 2, which is the same as 1/4. So our next coordinate's at negative 2 and 0.25. Then we have 2 to the negative 1, which is the same as what? Half, 1 over 2. 1 over 2 to the 1, technically, which is a half. So our next coordinate's at negative 1 and 0.5. Then we have 2 to the 0. What's anything to the power of 0? 1. So now we're at 0 and 1. Then say we have 1. It's going to be 2 to the 1, and 2 to the 1 is 2. And then we have 2 to the 2, which is 4. So now we're at 2 and 4. So if you look at this graph, it's actually getting big quickly, correct? It's growing exponentially. So we start off with something small, and then it grows quickly. So then, so then we would have 2 to the 3, which is 8. And then we'd have 2 to the 4, which is 16. It just sits there though, right? So what's going to happen is these are going to connect, and we're going to go this way, right? So we're growing exponentially because as we go from left to right, it's getting taller faster, correct? What's going to happen on the left side of this? So if I did -4, I would get 1/16. If I did -5, I'd get 1/32. So it's just going to get really, really, really close to 0, but it's not going to touch 0, right? It's going to be a really small decimal. So this will run along the x-axis, not getting higher, run along the x-axis, but not touching the x-axis. So it's going to get super close to 0, but not touch 0. So what actually happens is on the x-axis, if I'm not vertically translated at all, because the only thing that will make it that this graph could move down or could move up, right? And then I have x-intercepts. This one doesn't have any. So I actually have, on here, I'm going to put a dashed line on the x-axis. A dashed line means the graph gets closer and closer to it, but it doesn't touch it. It's called an asymptote. We talked about them last year in reciprocal graphs. This is a horizontal, because it's a horizontal line. It's a horizontal asymptote. On the x-axis, what is the equation of the x-axis? Y equals 0. So the equation of the x-axis is actually y equals 0, and the equation of the y-axis is actually x equals 0. So what's the domain of this exponential graph? Anything, right? It goes out left and right for forever. So for set notation, it would be x such that x is an element of the reals. For set notation, because it says the set of, the squiggly brackets, so that's set notation. And in interval notation, it would be negative infinity to positive infinity round brackets. What is the range of this graph? Greater than 0. A lot of people will put equal to 0. Is it equal to 0? No, that's where the dashed line exists, which means the graph can't exist. So it would be set of y values such that y is greater than 0. Y is an element of the reals. And in set notation, that would be round bracket, 0 to infinity round bracket. So it kind of looks like a coordinate. Yeah, because you can't equal infinity. Infinity is a concept. And then the asymptote is at y equals 0. And then does it have any x-intercepts, this particular one, unless it's moved? No. Does it have a y-intercept? That's 0, 1. Or net 0, 1. So our b value up here was 2, correct? Yeah? That is b is greater than 1. Remember, I have two options. My b value can be between 0 and 1. Guys, my b value can be between 0 and 1, and my b value can be greater than 1, correct? This one was a 2, so my b was greater than 1, yes? When your b is greater than 1, you give the shape above. This is called an increasing exponential function, or an why does it want an exponential growth function. I should say an exponential growth. So we're growing because it's greater than 2. What is the value of a on all three of these? 1. Like it'd be 1 times 1 times 1 times. Quiet, please. The value of b for this one is 3. This one is 4. This one is. So to be blatantly honest, the larger your b value gets, the faster it increases, correct? So the 5.25 has the largest exponential growth out of all of them. So it can be the closest to the y-axis as it is drawn. So like if I gave you a graph like this, and then I gave you a graph like this, and then I gave you a graph like this one has a smaller b value than this one, correct? Like the b value on this one would be larger than this one, because they're growing exponentially faster. So the closer it is to the y-axis, the larger b value it actually has, if they're all comparable. Now the y-intercept for all of these is what? 0, 1. And the reason why is if you want a y-intercept, you let x equal 0. So we're going to get y equals 3 to the 0. And what is 3 to the 0? Just 1. And then here we get y equals 4 to the 0, which is 1. And then y equals 5.25 to the 0 equals 1. So 0, 1. So how do different bases affect the function? It makes it grow faster or slower, correct? Close to the y-axis or not. Okay, next page. So now my a values aren't just 1, correct? This one has an a value of 1. This one has an a value of 3, 4, 5.25. Right? The b values for all of them, however, are what? 2. So they're all doubling. So the function itself has the same shape. They're all the same shape, because the doubling would make it have the same shape. But what are the y-intercepts for these? We would get y equals 2 to the 0, which is 1. So I would get 0, 1. This one I would get y equals 3 times 2 to the 0. And 2 to the 0 is just 1. 3 times 1 is 3. So guys, if there aren't any transformations but the stretch is your y-intercept. And it makes sense because your basic y-intercept of every exponential graph is 0, 1, right? 0, 1. So the only thing that can move that 1 is multiplying it by something. So your vertical stretch or translating it, but we don't have any translation. So this one's 4 times 2 to the 0, which is 4. And then this one is 5.25. All right. What happens if our b is now between 0 and 1? So this is the third, correct? The b's we've looked at have all been greater than 1. 2, 4, 5.25, right? This b value is between 0 and 1. So let's actually graph this one. So my new y is going to be 1/3 to the x. So this one's going to be 1/3 to the -3. It'll be 27 because how I can actually make that -3 be +3 is flip the fraction in the inside. Taught that in grade 10. So I get 3/1 to the 3, which is 27, which is too large. Because I'm going to make my x scale 1, my y scale 1. You should always tell your graph what it is. Okay, then here I'm going to get 1/3 to the -2, which is the same as 3/1 to the +2, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then here I get 1/3 to the -1, which is 3/1 to the 1, which is 3. And here we get 1/3 to the 0 equals 1. And once again, it's 0, 1 because we don't have an a value. We don't have a vertical stretch, right? Or, well, we do have an a value. It's just a 1. We don't have a vertical stretch. And then we have 1/3 to the 1, which is 1/3. So 0.333. And here we have 1/3 to the 2, which is 1/9. Then 1/3 to the 3, which is 1/27. And 1/3 to the 4, which is 181. Just means super tiny to the 1 to 0. But it's not still not touching 0, correct?
Nope.
So my graph, if I could read from left to right, it's starting large and then it's getting super small. So it is doing what this time? Decreasing. And my horizontal asymptote is still on the x-axis, which is the line what? Y equals 0. My domain is still XER. Still goes on for life out to the right and the left. The range is still greater than 0. The asymptote is still y equals 0. And the y-intercept, oh my gosh, y-intercept is still 0, 1. So, if 0 is less than b is less than 1, you get the shape above. This is called a what exponential function? Decreasing. Or an exponential decay. Now, what type of transformations occur between y equals 3 to the x and y equals 1/3 to the x? You cannot compare exponential functions unless they have the same base. So this one here is y equals 3 to the x. I need this one to be y equals 3 to the x. How do I bring this up here? If I flip-flop these, it would be 3, correct? What happens when I flip a fraction? What happens to my exponent? Turns negative. So we get 3 to the negative x. Correct? What happens when you have a negative in front of the x value? It's a reflection in the y-axis. Okay, let's look at this one. We have negative 2, 16. Negative 1, 4, 0, 1. These are going up by 1, correct? Are those going up by 1? My y-intercept is 0, 1, so what's my a value? 1. What's my b value? What's happening from here to here, here to here?
It's decreasing by, I think it's 0.25.
Yes. So it's dividing by 4 each time, which is multiplying by a quarter. So you get 0.25 for a quarter x. So your homework is to finish those questions in that booklet up to question 5.